I'll be your host for the evening. And so I'd like to welcome not just the Sigma members, but also our affiliated club and society members of Highland Astronomical Society, Aberdeen Astronomical Society, Caithness Astronomical Group, Dundee Astronomical Society, and also North Ronald Sea. Okay. And of course, any first-time visitors we got tonight, and a special welcome to all our new members that we've had joined in the last 3 weeks. You were all very, very welcome. Just before I start, I want to talk about the extra meeting that we're going to be having in, we're going to have an extra Zoom meeting this month on Friday, the 16th of February, obviously. This is Hazel Collett from the BAA. She was due to talk to us in April, but due to personal circumstances, she was not going to be able to make that. So rather than lose her presentation, it was decided that we would do an extra talk this month. And I say that will be held on Zoom on the 16th of February. A link to that will go out to you very, very soon. Her talk is actually The Beauty and Violence of the Sun. And say the link will be sent to you very, very soon for that one. Okay, so make a note in your diary for that. So the next thing we need is I've got a little thing I need to do with Tim. So if Tim, would you like to join me, please? He's panicking about this. I know he is. Okay, Tim, can you turn your microphone on as well, please? Now, many of you will know Tim. Let's say, but many of you won't, especially the sort of new members, especially for that. Tim is one of the 2 club presidents, and he's been a member since the club was formed 24 years ago. In fact, he is number 1. Okay. So his membership number is actually number 1, and he's very, very proud, and I may say protective of this number. I'm going to tell this story once again, Tim, because there's new people here who haven't heard it. Back, I think it was 2017, 18, we were talking about changing the membership numbers to try, because it got a bit messy with people leaving and coming and going. So we were going to do the membership. So the first member who joined in like this year, 2024, would be 0124. And I was at the committee meeting, it was a live committee meeting, I could just see Tim cringing a bit in his seat there, and he went, "Oh, I don't know about this. I really don't know about this." He said, "Because I'm number 1, and I want to keep my number 1." So it ended up being, well, we kept the old system and operated the new system at the same time. So we've now got 2 systems running. But say, yeah, we couldn't leave his, we couldn't let him lose his number 1 status. As I say, Tim's been a president, is a club president, and he took that role on asking, well, what does it involve? I remember you saying with this, and it was basically, you were told, well, it's an advisory role, and you've not even got to attend the club meetings if you don't want to. But he does, and most of the times he sort of enjoys them as well, I believe. I did say, but he does a lot more than that for the club. He partakes in many meetings, organises quite a few things in the meetings. He does a lot of outreach work, and he's a great ambassador for the club. It's a brilliant job that he does for us as our president, along with Bill Leslie, our other president as well. Let's say Tim gives the club what I call a stable platform, and that's going to aid Sigma as we go forward in the years to come. It is a brilliant job he does, along with Bill. As I say, he's been doing this now for 24 years. And a discussion was had in committee that you don't know about, to how we could recognise this feat that you do. It was decided that in recognition of Tim's outstanding and dedicated service to Sigma over a long period of time, on behalf of Sigma, I would like to offer you honorary club membership. So Tim, thank you so much for everything you do for us. And would you like to say a couple of words, please do.
Oh, well, thank you. This is totally unexpected.
Well, it might be.
I just been out this afternoon busking to be able to pay the next subscription.
Sure.
But that's a lovely thought. Thank you so much to you and the committee. I don't recall a Zoom request coming through for a committee meeting, so that must have been very secretive.
It was all behind closed doors, and that's why I couldn't say much until about 2 minutes ago before we went silent online, and you started itching in your seat thinking, what's going on?
I was wondering what was going to happen. But thank you so much. I really appreciate it. I think when the famous four, that's myself, and Richard Pearce, Mike Ross Newland, and Sir Alexander, decided it might be a good idea to start a club. Little did I think back then that we'd still be going strong and heading into what will be our 25th year next year. So we'll have to start thinking about ways to celebrate that. But I really appreciate that, to you, to the committee, and to all the members. I very much appreciate it. That means a huge amount to me. I'm lost for words. Thank you so much.
You're more than welcome, Tim. Thank you very much for everything you're doing. Okay, anyway, on to tonight. So helping me in the background, I've got Rich and Mick, who's going to be the Zoom co-host. So if I suddenly drop out, he'll take over. In this, say, Chris is there as well. He's handling the Q&As, and I'll explain how to ask your questions in a little while with these Zoom controls. If you're new to Zoom, I know some people might be, I think we've all used it for quite a while now, but if you want to ask any questions to any of our speakers tonight, in the little Zoom bar, you'll see a Q&A button. If you click that, you can put a question in there at any time you want to. And Chris will keep an eye on that, and he will ask the questions over to Brad at the end of Brad's presentation. Okay. Just a little note for all the panelists and everything, and make sure your mobile phones are turned off, because it gets very, if they start ringing, it gets a bit embarrassing for us all. So the meet and brief, for those who haven't been to Sigma before, they say we have the main talk tonight. It's going to be by Brad. They say Chris will do the Q&A, and Tim's going to be doing the vote of thanks. That was why I asked him to come and do the vote of thanks today, so I made sure I had him on the screen. Then we have a little 10-minute break. This gives us a chance to get set up for the second half. And then in the second half, Ray's just going to talk a little bit about the workshop that we're running on Sunday. He'll tell you all about that. Then there'll be a couple of members' photos, and then the Morning Sky at night with Nick. And then a little bit of club news to finish off. So we might overrun a little bit tonight, but it doesn't really matter because we're on Zoom, so you can get up and have a break at any time you want to. Okay, tonight it gives me great pleasure to welcome Brad Gibson. This is Brad's first time giving a presentation to Sigma. Are you there, Brad? Make sure you can turn your...
Indeed, I am.
Coming on, you are. It says this is his first time giving a presentation to Sigma, and tonight we'll be diving into the world of cosmology, and he'll be talking about the end of the universe. What can I tell you about Brad? Well, in his own words, he is an Aussie-Canadian transplant. He is the head of physics and maths and director of the E.A. Milne Centre of Astrophysics at the University of Hull. Brad was responsible for the first defining the Milky Way galactic habitable zones, named a top 10 news story of the year by the National Geographic, determining the expansion rate of the universe, for which their team was awarded the Gruber Prize in Cosmology, and building the world's first liquid mirror telescope observatory. His 1,000 plus outreach events over the past 7 years has reached more than 2 million people around the world, including more than 100 schools and colleges around the UK. His commitment to widening the participation and diversity and improving the career prospects of physics students led to his changing Changing Face of Physics campaign being named the best practice in the country by the UK's Equality Challenge Unit. You're a busy man by the sound of it, Brad.
And a very
So
forgiving wife.
So everyone, would you please welcome Brad Gibson from the University of Hull. Over to you, Brad.
Thank you very much, Pete. Let me just do my share and
got that.
Get that out of the way, and hopefully
that's looking good. That's looking good.
That
Over
looks
to you.
okay. Excellent. Make you a little bit smaller. So thank you very much for that. There's not very often when I give a talk and think I really wish I could be there, but boy, this is one that I really wish I could be physically up there, right at the north of Scotland with you. It is a dream to get back there. It's been a couple of years, and the next time I'm up there, I'm going to track you folks down and see you all in person. So thank you very much for the invitation. This talk, I guess it kind of sprung out a little bit from what Pete was saying in the introduction, and I spent a number of years working with the Hubble Space Telescope, working on the expansion rate of the universe, the so-called Hubble constant. And almost by definition, what we do in astronomy and astrophysics is looking back in time. What was the expansion rate in the past? Was it accelerating in the past? How did galaxies form and evolve? It's by definition, we look backwards in time when we use our telescopes. And I spent a number of years thinking about that question. How did the universe form? How did it get to where it is now? But I hadn't really spent a whole lot of time thinking about where it's going, what the ultimate fate is. And it came up during one of my lectures at university, and someone asked me that, and it made me sit down and do a little bit of research and digging into this question. It's a fascinating one that hasn't got the same amount of attention, obviously, as looking backwards in time. So that was where the idea germinated, and that's what I'm going to spend the next 40 minutes or so covering. But I did want to spend just a couple minutes just to say a little bit about who we are here, because it's my first time talking with you, and many of you may not have ever been to the University of Hull or visited this part of the country or know who we are. So just a little bit of history as to who we are to give some context. I was surprised when I came to the university. That was now 9 years ago, I guess now. I didn't know a lot about the university, didn't know a lot about the region. I think because at that point in time, there wasn't any astrophysics here. And so from a work perspective, I'd never really given much thought to visiting. And I came out they put out an ad looking for a professor of astrophysics, and were clearly interested in growing that. So I threw my hat in the ring and came out without really knowing much about the place. But I fell in love with it. The campus is lovely. It's one of the oldest universities in the UK, and its architecture is kind of traditional red brick, literal red brick uni, without being part of the Red Brick University Club. So it's a lovely little campus. It was the City of Culture in 2017, the UK City of Culture. So there was a lot of investment in fixing up kind of some of the surroundings. It's still a North England city with its rough spots, but it has really transformed over the last decade. And it does have, from my perspective, a rich scientific history. If you've ever played with Venn diagrams where you overlap things, John Venn was from Hull and was here for many, many years. Arthur Milne, the namesake of our center, I'll say just something about it in a second, is also from here. And that liquid crystal display technology that many of us use and take for granted nowadays was invented here at a time when I don't think the university fully appreciated the potential power of a patent, and they missed out on huge opportunity to bring in a fair bit of money on something that they probably didn't fully appreciate at the time, that we all now take for granted everywhere. And something that I also didn't know about the place was I guess just a few years ago, we had the 50th anniversary of Apollo 11, and I started getting contacted by various newspapers about the role the University of Hull played in that very first moon landing. I didn't know anything about it, so I had to start Googling around. I didn't know that this was the case, but those first little grains of sand, call them moon rocks if you like, that were brought back, were actually brought here to the University of Hull for analysis, not to sort of the the big famous places and the Harvards and Caltechs of the world in the US. But at that point in time, in the late 60s, early 70s, the physics program here was, particularly the applied physics, geophysics program was, if not the world leader, one of the world leaders. And so those very first moon rocks that were analyzed, their characteristics, reflectivity, all the sorts of things that we now sort of take for granted, that was actually done here. And that was a shock and a surprise to me. It's something that we've now embraced very much now that I am aware of it, in terms of the things that we've got on display outside my office. And one thing I want to start with, I'm the director of the E.A. Milne Center for Astrophysics. E.A. Milne, our namesake, is not the same as A.A. Milne, Alan Milne, the creator of Winnie the Pooh. I get asked this question a lot when I'm sitting on planes or trains and people see me typing away furiously and they see Milne Center. I do get asked this question a few times a year, particularly when I'm traveling, asking, what does this have to do with astrophysics? So they do have some interesting history. They're not related in any way. But Arthur Milne was born and raised in Hull. It's a fascinating story. When I moved here 9 years ago, his daughter, Meg, had just published a biography about her father. It was an interesting character who had early onset Parkinson's that wasn't recognized. He wanted to serve in the military during World War I, but he couldn't because of his health. And so he was seconded to the Navy, and he was one of the primary developers of the first anti-aircraft gunnery technology, using his knowledge of stellar atmospheres, but applied to the Earth's atmosphere, and using echolocation and how sound propagates differently depending on the barometric pressure, and would able to use effectively triangulation by sound to feed that information to gunners on the ground. So when you look at his Wikipedia page, you see actually more about that than all of the work he did in alternate theories of relativity, if you liked. He was a contemporary of Einstein. They were very good friends. He was a very clever mathematician, and Einstein had a lot of respect for him. He had his own version of cosmology, but was wildly incorrect, but it was beautiful mathematics. And he's one of the best known cosmologists in history, after Einstein and a couple of other ones. And it was just fortuitous that it turned out he had been born and raised in Holland. I was able to reach out to his daughter, Meg, and she was pivotal. And if you can see my cursor moving around, my mouse moving around, that's Meg sitting down there in the bottom right, his daughter, who was here with us to launch the center sort of 8.5 years ago. And we've grown from 0 staff and students up to 40 staff and postgraduates, one of the largest research centers in space sciences in the north of England. So yeah, we're very, very proud of how it's developed over the years. And I'll just end by saying, echoing a little bit what Pete said, I think when I first got here, the thing that really struck me was the very grim diversity mix in our undergraduate physics program. It's not unique to Hull. It's pretty much endemic around the Western world. Typically 20% of the first year cohort doing physical sciences are women. And so a real focus for me when I got here was doing what we could do to try to rectify that, and do at least as best we can. It's a multifaceted problem. There's no simple one solution to it. And so we had this multi-pronged approach under this umbrella called the Changing Face of Physics. And I was fortunate to have a number of students at the time who were first year students within physics and astrophysics who shared that passion to try to change our diversity profile. And that's some of them there. Most of them, all 5 of them stayed on to do PhDs and postgraduate masters. We've had a further generation, because diversity is more than just gender, BAME, LGBTQ+. And so a second generation, and now the newest generation who've just arrived, who are helping again, coming into schools and colleges with me, being peer role models for the next generation of scientists, all the way from nursery and primary through secondary and college. And so their contributions really ultimately would have transformed us from being 10% of our first year cohort being women to last year being 45%, which is the highest anywhere in the Western world. So more than the research we do is probably the thing we take the greatest pride in. And one of the perks of doing not just this, but what it is that we've done in the region, which is the poorest city in England in terms of socioeconomics, As we do have a lot of like-minded people who have helped us, astronauts like Michael Foale and Steve Swanson, Helen Sharman, who's from Yorkshire, not too far from here, is a close friend and works with us in a number of events, and will be coming back to talk to school kids in July in her next visit. Jocelyn Bell Burnell, the discoverer of pulsars, and Brian May, maybe most famously a guitarist for Queen, although when I talk to my kids and primary school kids, they don't really know who that is, but the teachers and you and I all do. I've been very fortunate. They're not just celebrity names. They do share passion with trying to widen participation and reaching out to school groups and schools who don't normally have the opportunity to engage with some of the things that we do. So they've been also invaluable in changing our profile here. So I wanted to take sort of 5 minutes just to give you a little background, just because you wouldn't have seen any of this before. So thank you for letting me do that. And now let's turn to sort of the sciencey bit of the talk. I'm not going to leap straight into what's going to happen in the future, because I just want to give a little bit of context by looking backwards in time. You need to sort of understand a little bit about the past before we start projecting forward in time. This is probably one of the most used and some could say abused image in probably all of astronomy. It's almost every talk on cosmology uses this particular one, and I'm not going to be any different here. It captures the essence of the universe in a single slide. And over the left, I'm not going to talk about really the formation of the universe. You're getting into hardcore mathematics that goes above my head. But we've got this, this incredibly dense, hot universe, and sort of spread through there, you've got little quantum fluctuations, and something kickstarts that Big Bang, and there's a rapid inflation, and you go from being something that is incredibly hot, incredibly dense, without really anything in it other than really simple chemical elements, hydrogen and helium. Not much else has happened in those first few minutes as the universe is going through this rapid inflation. And then the universe is so hot that this hydrogen and helium, most common elements in the universe, let's just think about hydrogen as a really simple one. It's one positive charge, a proton, and one negative charge, an electron. And normally they're stuck together. When it's really hot and really dense, the electron gets pulled off, and all the electrons and helium atoms get pulled off. And so what happens is you have this sea of electrons in this really hot, dense universe that is rapidly expanding, but all the electrons are floating around, and they kind of act like a cloud. The energy from the Big Bang, the light created by the Big Bang, it actually can't move very far because it keeps, if you like, running into all of these electrons. But as the universe continues to expand and expand, it cools down, it cools down, it cools down. And eventually, after a few 100,000 years, that sea of electrons, that fog that's blocking the light from the Big Bang escaping, those electrons reconnect back onto their hydrogen and helium. And that lifts the fog. And that energy, the photons from the Big Bang, can then stream freely across the universe. We can look back in time and we can see this, what's called the cosmic microwave background. This is the whole sky image in temperature. And you see this mottled pattern of red, which is a little bit hotter, and the dark blue, which is a little bit cooler. But there's slight temperature differences in this cosmic microwave background. And those temperature differences, you can trace them back to the quantum fluctuations I started about. And these slight temperature differences ultimately form the seeds for the galaxies that form and evolve as time goes by. So on this cartoon, as you move across to the right, you get closer and closer to today. You start with small galaxies forming, and they come together to form slightly bigger ones, et cetera, et cetera. And so it sort of captures the essence of the universe from a small, hot, dense thing to what we know and love today. And we can look at that cosmic microwave background. We can look at how galaxies like our Milky Way, how they rotate. We can count the number of galaxies as we look back further and further and further in time. We can take all of that information, and it tells us that roughly about 15%, 1 part in 7 of the matter, the stuff in the universe is normal, like the stuff that we're made out of, and what we call baryons, hydrogen, helium, carbon, iron, silicon, all the chemical elements that we know and love. But then there's this big part, this 6 parts in 7, the 85% is dark matter. Can't see it, but we can feel its influence on in the way that it bends light and causes galaxies to rotate. But we have this kind of a beautiful picture using these different observations that allow us to pin down just how much matter is normal and how much of it is dark. It doesn't tell you what that dark matter is. We may come back to that towards the end, but we've got a pretty good accounting of what the matter content of the universe is from looking at these sort of observational data sets. Now, ignore the stuff on the right. What I just want to show you is this is the same picture in some sense, but turned vertical instead of horizontal. The Big Bang is at the bottom. The present is kind of in the middle where we are today. And it's kind of a cartoon representation of what we think is happening with the universe. Now, if you start down at the bottom, you see the Big Bang, and the universe is starting to expand. And if you got good eyes, you may be able to see as you move into the orangey red bits, it actually, towards the top of the yellow, it looks like it's starting to slow down. And the orangey red bits, it almost looks like the universe is starting to pull back together again. That's kind of what you would expect if a universe was, if there was enough dark matter, if there was enough gravity being generated by the matter content of the universe. As the universe is expanding, if there's enough matter, it'll slow it down and slow it down. And maybe if there's just enough, it might pull it back together again. And so when I was doing my PhD 30 years ago back in Canada, we were still debating about this. Is there enough matter to pull the universe back together to have a big crunch in the future? Because the data, it kind of looked like that might be the case. But as we got more and better, more precise, accurate data, looking back further and further in time, we actually realized that no, it's not closing in. It temporarily looks like it was closing in the universe, but then something 5, 6, 7 billion years ago changed, and the universe started to accelerate again and rapidly expand. And so we have this, we use the terms dark matter because it's like gravity, it pulls things in. And so dark matter constrains and seemed to be pulling the universe together. And then something changed in the universe. Sometimes they talk about a phase transition, but the words don't really matter. But something kicked in that pushed against the gravity and started to repel everything and allowed the universe to start accelerating and accelerating and accelerating. We call this dark energy. Dark matter is a mystery. Dark energy is even a bigger mystery. We know, if you like, how much there is, just like we know how much dark matter there is. We know the impact that it has. We just haven't sort of pinned down what specifically dark energy is, what dark matter is. But we are at a stage now where the observations back up what I've just said, that it looked like it was pulling together and then dark energy kicked in and has started blowing it apart. And as you look in that cartoon, it goes to the future and it looks like it continues to expand and accelerate. And that's what we're going to talk about in sort of the remaining half hour, is looking at a few signposts along the way, and whether this actually is going to hold, for infinity as we go forward in time. To give some of those numbers as we look back in time, some signposts, just to sort of some numbers to have in the back of your head. You've got, this is, now on the right, Big Bang there on the left. The bulk of our Milky Way galaxy and the Andromeda galaxy, most of the galaxies around us, yes, they're continuing to form today because they're still accreting objects and continuing to grow in some sense. But the bulk of the Milky Way, the bulk of the galaxies around us formed 9, 10, 11, 12 billion years ago, the vast majority. Our solar system, the sun, again, it's not a hard, fast number where it says this is when it started and this is when it finished. But, 5, 6 billion years ago is when our solar system started to come together and the sun became a nuclear fusion burning object kind of 5 billion years ago or so. So there's that window in there where the sun and the solar system formed. Life on Earth doesn't spontaneously appear. Planets are not hospitable places for life for 1 or 2 billion years. So the first single cell life appeared about 3.5 billion years ago. And mammals, us, we're only a couple 100 million years ago. That's, a tiny little dot on this entire timeline. And Homo sapiens, we're only a couple 100,000 years. So we're a fraction of a pixel on this screen there, right there on the right. So we have been around just, you know, a tiny little window of this timeline. And there's lots of things during the past and today that could have wiped us out. You could have a whole talk on all the kinds of ways to die. And I will talk about this in an astrophysical sense in a couple of minutes. And there's, you know, whole talks on societal, socio-political, self-destruction, pandemics, all kinds of things that could have knocked us out and have come close to knocking us out over these last little period of time. But that's topic for another day. Again, looking backwards, there's a number of things that have the potential to knock us out. We've been a bit lucky in some sense. Again, I'm not going to spend a whole lot of time on these, but you know, every few 100 million years, we go through a spiral arm. On the left is our Milky Way. If you could step out and look down on top of it, this giant pinwheel. The sun sits halfway out in the disk between spiral arms. There's not much around us. All the stars are moving at 500,000 miles per hour in nice circular orbits. And we're more or less all moving lockstep. But we're not moving exactly the same speed as the spiral arm. So again, every few 100 million years, we do catch up to the spiral arm and we pass through it. We go from a place where there's not much around us, like today, to a region where there is a lot of stuff around us. And that can jostle our solar system. It doesn't bug the planets, which are little circles that you see there. And if you've got really good eyes, the bottom plot, there's a tiny little blue box. That's where the planets sit in our solar system. Our solar system is surrounded by billions, if not trillions, of comets called the Oort cloud, all loosely held on by gravity. And when you pass through a spiral arm, it shakes our solar system. It doesn't bug the planets, but it does shake loose comets. Some fly out, some fly in. These sorts of things do happen. It happens around other stars. It's not unique to our sun and our solar system. These sort of things do happen, and they do happen every, you know, a couple 100 million years. And so, you know, we've played the statistical game. We haven't been wiped out yet, but, you know, we've had some close calls along the way. You can go back 65 million years ago. The big impact event took out the dinosaurs and about 80% of the species, I think, that were existing on Earth at the time. So this is something that does happen. And in some sense, we're a bit lucky that it hasn't wiped us out. And it's not just us. You can look at, many of us might remember, what, 30 years ago, Comet Shoemaker-Levy got absorbed, ripped up by Jupiter and left its debris across the atmosphere there that you can see in that panel to the left. You know, so these things do happen. And Shoemaker-Levy was a big one. It's about a mile across in size. That's the kind of event that might not, you know, wipe out planet Earth, but it would have been a pretty important species killer if this gravity hoover that Jupiter is kind of a protective shield that absorbs some of these comets as they work their way into the inner part of the solar system. But that's a mile across. You know, it's smaller than the 10, 20-mile comet that took out the dinosaurs 65 million years ago, but it was still pretty darn big and would have caused a whole lot of damage if Jupiter hadn't been there to intervene on our behalf. And more recently, you know, it was about 10 years ago when the Chelyabinsk meteorite impacted in Russia, and there's all kinds of great dash cam videos and all these sorts of videos of damage that was done by this particular event. The reason why I throw Chelyabinsk in, that was a small one. You can see the windows getting blown out. It was only about 10, 15 meters across in diameter. So a tiny little thing in the grand scheme, did a whole lot of damage, but I've actually got a little piece of the Chelyabinsk meteorite sitting in my hand right now that I like to show off every once in a while. And not only that, as you pass through a spiral arm, not only do you get shaken and potentially get blasted left, right, and center by comets and things coming in, as you pass through a spiral arm, that's where big stars today are forming. They don't form around us. They form in the dense regions of spiral arms. And big stars, they live fast, they die young. They're important because everything you can see, everything we're made of, came from stars. You know, the carbon, the iron, the silicon, the magnesium, nitrogen, oxygen. It all comes from these exploding stars. But like any explosion, if you're too close to one when it goes off, you know, the bad can outweigh the good. So as you pass through spiral arms, you have to be a bit lucky and hope that one doesn't explode near you. And we did have that about 10 million years ago. We were close enough to one exploding star that the wave that you see propagating outwards there on the right actually swept over planet Earth, and it left a thin layer of radioactive iron. It's called iron-60, super thin layer that covers the entire planet Earth. It only comes from exploding stars. So we know that we were pretty darn close to an exploding star about 10 million years ago. Not close enough that it wiped out our biosphere, but it's still uncomfortably close. So we're playing, again, we're playing the odds here in being able to have this talk tonight, and that we've been able to survive these various astrophysical things that seem to be conspiring against us. So that's a little bit looking to the past and how we're a bit lucky to be here today. So what I want to do for the next 25 minutes is just walk through some of the interesting things that are coming over the next thousands, millions, billions, trillions, quadrillions of years. It's not comprehensive. I've tried to pick out some of the interesting signposts and things to look forward to as we move forward into the future. So I'm going to start not too far into the future, far enough that you and I aren't going to lose any sleep over it. This is roughly about 10,000 years from now. Antares, I think that's I looked it up recently, I think it's the 16th brightest star in the sky. I think if you're up in northern Scotland, you're never going to see it. I think here in south of England, just tickles the edge of the horizon once in a while, but it's very prominent in the southern sky. It's about 600 light years away, so it's far enough away that when it does explode in X thousand years, it's far enough away that it's not going to cause us any damage to our biosphere. You would have to be sort of 20, 30 light years away to really wipe out life on Earth. So it is far enough away that we don't have to lose sleep over. It'll be outside of the sun and the moon, far and away the brightest thing in the sky. So if you are around in 10,000 years, you're going to have a spectacular view of what used to be Antares. 300,000 years from now, another star is predicted to explode, plus or minus a little bit. 300,000 years. It's also a very heavy star, something like, lost track now, probably 40, 50, maybe 60 times heavier than the sun. It's called a Wolf-Rayet star. It doesn't have an exotic name. It's just WR for Wolf-Rayet 104. It's really far away. It's 10 times further away than Antares, 7,000 light years away. So again, you might think of it, if Antares isn't going to cause any damage, when this thing explodes, it's even further away. There's no way it's going to cause any damage. But it's got a lot of attention over the last sort of 5 to 10 years, because the way this thing rotates and spins, there's some reasonable arguments have been made that this is going to explode, as heavy stars do, but it's going to be a special one. It's called a gamma ray burst. And gamma ray bursts, they are exploding stars, and roughly, I don't know, 1 in 1,000, 1 out of 10,000 exploding stars explodes in this special way called a gamma ray burst. Unlike the little cartoon I showed you of this wave coming out in a nice sphere around an exploding star, a gamma ray burst takes 100 times the energy, but instead of allowing it to go out in a sphere, it focuses all that energy into these jets, these beams that come blasting out, if you like, of the North and the South Pole. And so if one of these gamma ray bursts explodes near you and you're to the side of this drawing here, artist's representation, it's fine. These gigantic, powerful beams they miss you. You don't want to be caught up in the beam, because then even if you are 7,000 light years away, if that beam is pointing at you, it has the energy, more than enough energy, sufficient to evaporate our biosphere. And it got a lot of attention a few years ago because there were some observations and some predictions made that this thing, the way it was spinning, the direction they thought it was spinning, that this beam, when it does go off in 300,000 years, is pointing straight towards us. So you can Google it. You can find lots of press releases talking about this is going to be the destruction of planet Earth in 300,000 years. Now, it hasn't really stood the test of time. The more recent observations over the last 2-3 years have suggested that, maybe that was an overly enthusiastic interpretation of the data, and we don't really have a solid feel as to which direction this jet is going to go off. You can take a step back and say, look, don't even bother trying to do that. Let's just assume it's completely random, and the jet can go off in any sort of direction. And you can, given the distance that it is and how the jet comes out in this sort of cone, you can say, look, if given the distance and the shape of the cone of these jets, if this cone is within, plus or minus 12 degrees of pointing straight at Earth, it could mean the end of the biosphere. And so even if you don't know which direction the jet is really going to go, you can just play the random game and say, look, there's a 7% chance we will be within 12 degrees of this Wolf-Rayet jet when it does explode in a few 100,000 years. So it depends. It's a glass half full, glass half empty, or optimist versus pessimist. There's a 7% chance. So that this thing will wipe us out. There's one chance in 14. So yeah, if you're an optimist, 93% chance it's going to miss us. But there's that 1 in 14 chance that when this thing goes off, we will be caught up in that beam. So that has the potential to wipe us out. And then what happens to the universe after that becomes irrelevant in some sense. But let's assume we get through that one. Some people have suggested that this is the sort of event that sort of 450, 500 million years ago, the late Ordovician period, that was an even bigger mass extinction event on Earth. So some have suggested, based on weird chemical isotopes, that it might have been one of these gamma ray bursts. I don't believe it myself personally, but there are some who think that might have been the case. But again, I would take that with a huge grain of salt. Okay, let's jump ahead 1 million years from now. What I said previously about as we pass through spiral arms, we shake our solar system, which shakes loose, potential to shake loose lots of comets. Basically, anything that shakes our solar system can do that. And we know that this happens every few 100 million years as we go through the spiral arms. But other things can do it. And so here's a star in the sky, Gliese 710, otherwise sort of innocuous. It's about half the mass of the sun. But unlike all the other stars around us that are effectively moving all in the same direction in lockstep around the galaxy, something has nudged the orbit of this star. So it is now coming straight towards us, kind of like a bullet out of the barrel of a gun. It's coming at 30,000 miles per hour. In 1 million years, this star is going to pass through our solar system. So if you are around in 1 million years, again, other than the sun and the moon, it will be the brightest thing in the sky, one of the fastest moving things in the sky as well, as it sort of passes through our solar system. Again, it's not to the inner part where the planets are, but it will pass right through that Oort cloud, and the gravity of the star is going to shake loose a lot of comets. And the best guess that people have been doing over the last couple of years modeling is that about 10 million comets are going to get shaken loose, and some of them are going to escape, but the vast majority of them are going to come raining down to the inner part of the solar system. So you have to hope that maybe Bruce Willis is around in 1 million years' time with some sort of Armageddon thing with shields up to protect us, or the disembodied head of Elon Musk might be around to have some sort of technology shields in place to block these comets that are going to be raining down in us. But if I was going to guess, if taking us out of the mix, what sort of astrophysical thing might have the most likely potential to wipe out everything on Earth and wipe out Earth itself? It'll be this in 1 million years' time, when you've got 10 million comets raining down to the inner part of the solar system. Yeah, the solar system is mostly empty space, and most of them are going to miss us. But you throw 10 million comets at us, there's a non-negligible chance that that's the sort of thing that could wipe us out. And you can jump, now we're going to race forward in time a little bit, 100 million years from now. Even if we do get through that this event in 1 million years' time, you are still playing the statistical game. Like I said, every 100 million years, couple 100 million years, these sorts of close encounters that shake loose lots of comets happen, whether it's a star passing by or a giant molecular cloud or passing through a spiral arm. These sort of mass extinction events, they're not perfectly periodic, doesn't happen every time, no matter what some people in the literature say. But again, you're playing that statistical game that this is going to happen again. There will be another mass extinction event. Maybe it's 100 million years, maybe it's 200 million years. But these sorts of things do happen. You can go 250 million years from now, and you might ask, well, let's say we have navigated our way through all this. What does Earth actually look like? Well, it looks really different in 250 million years. One of my favorite movies is this one, showing the plates on planet Earth, how they move around. And some are moving, most of them are moving very, very slowly. Australia is moving at an insane speed. It's something about moves about 1 meter every decade. So as we flip over here, here's Australia. For 50, 60 million years, Australia is already blasted into the side of Southeast Asia. It moves so fast, in fact, that things like GPS that we take for granted here don't work in Australia. So you have to have all kinds of corrections for GPS to take into account the fact that the continent of Australia is moving so fast. And as this movie runs forward in time, you'll see even the Antarctic moving its way up now to nestle in between Africa and South America. It slowly works its way up. It takes a couple 100 million years. But after about 250 million years, basically you end up having one sort of mega continent. Here comes the Antarctic working its way up. So you end up with one sort of mega continent sort of wrapping its way around call it the equator region of the Earth. The moon will have drifted out 6,000 miles further than it is now. So our day will no longer be 24 hours, it'll be 25 hours. It'll be a very different place in 250 million years. It'll look really different than what it does now. More like a kind of a water world thing where you've got all the Earth, the land is going to be concentrated in this mega continent around the poles with nothing much above or below. And what's happening to the sun during this time? Well, 500 million years from now, this is it's a kind of a boring plot, but where all these lines cross in the bottom left, that's today. And that's how bright the sun is today. If you go forward 500 million years, so it's just moving over a little bit on this plot, and you ask, how bright will the sun be? How luminous will the sun be? Well, it'll be about 5% brighter. So it'll be about 1 part in 20. It may not sound like a lot, but that's enough to really start driving the moist greenhouse effect. So in 500 million years, the average temperature on Earth will be about 50 degrees centigrade. And even in 1 billion years, it'll be about 80 degrees centigrade. So in that time scale of 500, 600, 700 million years, even if somehow we're still around here on planet Earth, we won't be able to live on the surface. It'll have to be subterranean. Maybe you can go to the poles. It'll be a little bit cooler, but there's no land there anymore. So it'll be some sort of water world sort of event. So again, if we are around in 500 million years here on planet Earth, very, very different existence than what we have today. And playing this statistical game as well, there's still this chance, every 500 million years, one of these gamma ray bursts is probably close enough and in a random angle sense has the potential to wipe us out. Again, it doesn't mean it will happen, but statistically, these things do happen every 500 million years or billion years or so. A gamma ray burst can hit us. 3 billion years from now, the moon is continuing to drift away, kind of a centimeter a year, whatever the number is. So in 3 billion years, the moon will be 75,000 miles further away than it is now. So it's about 30%, 1 part in 3 further than it is right now. And so, you lose all kinds of things like certain total solar eclipses and all kinds of other interesting things. But more importantly, in 3 billion years, with the moon being that 30% further away, one of the real benefits of the moon is that we've got this big, heavy anchor that goes around us every month. And one of the things that we don't appreciate is it keeps our orbit really stable. So as the Earth goes around the moon, the North Pole is not pointed straight up, it's tilted over. That's why we have the seasons, etc. But as the Earth goes around the sun, it's very stable. It's called the obliquity. It's tipped over by 23 degrees. It's really, really stable. And the reason why it's really, really stable is because the moon, as it drags the moon around, it does provide that stability. No other planet in the solar system has that. Our planet is unique in having a big, heavy moon that keeps its orbit stable. But as it drifts away, its influence reduces. And so the Earth becomes more almost like a bowling ball going around the sun, not at that sort of speed, but you do get wild climatic changes because we don't have that stability that the moon provides. It's probably one of the myriad of ingredients that are important for the development of complex life. Not the only one, but one of them. At the same time, 3 billion years from now, the sun will be 40% more luminous than it is now. The average temperature will be up a few hundred degrees centigrade. It'll be hot enough to start melting rock. So even if we are still around at that point in time, we're not going to be living anywhere near the surface and probably not anywhere on Earth because we're not suited for 200 or 300 degrees centigrade existence. 4 billion years, let's say we get through all these things. What's it going to look like outside? Well, the night sky is going to look very, very different. We've got our nearest galactic neighbor, Andromeda. It's moving towards us at about 100 miles, let's say roughly about 100 miles per second is roughly the number, but 250,000 miles per hour is the speed that it's moving towards us, which sounds like a big number, but it's very far away. But we're approaching each other. And in sort of between 4 or 5 billion years from now, these two galaxies are going to combine. You can see that in the simulation here, the animation that's showing in the bottom. And what's going to be left over is not two beautiful grand design spirals that the Milky Way and Andromeda are. You'll have probably a giant elliptical galaxy. So if Earth is still held on to the sun, which it should be, yes, it'll be very hot and very unpleasant. But if you did step out onto the surface of the Earth and look up, you're not going to see the Milky Way on a dark night. You're just going to see sort of stars kind of everywhere because it's an elliptical. There's no preferred disk anymore. So the Milky Way will not exist. It'll just be this spheroidal star of galaxy of stars. 5 billion years ago, yeah, we run into more problems with the sun. The sun runs out of hydrogen fuel, stops nuclear fusion, becomes a red giant, and Earth and Mercury, Venus, Earth all get incinerated. Now, again, maybe if we're still around, maybe we'll have the technology, we can push the orbit of Earth out to Mars or beyond and avoid the incineration of the planet at that point in time. But it counts on us having the technology to do that. If otherwise, Earth is wiped out in 5 billion years. So some of what follows becomes a little bit of a moot point, but there you go. 8 billion years from now, the sun has finished going through its red giant phase. It ends its life as what's called a white dwarf. There's nothing burning anymore inside. There's some residual heat that takes a few billion years to get rid of that heat and ends up crystallizing into effectively an Earth-sized diamond. You can read the number. It's worth about 1 billion trillion pounds. So you could buy planet Earth a billion times over relative to the Earth's gross domestic product. That's basically what the sun looks like in 8, 9, 10 billion years from now. Now we're going to really leap forward for the last few steps. 100 billion years from now, let's just say somehow the Earth is still around and wasn't incinerated. We've moved it further away from the sun so that it wasn't incinerated. One of the beautiful things about the Earth, and one of the things that again makes it special and is probably a really fundamental ingredient for the development of life, is we have this hot molten core. Some of that heat is left over from when the planet formed. A lot of it is also from radioactive elements that sit down in the core that keep it hot and keep it, this iron core really hot and molten and churning and rotating. And that's what generates our magnetic field. It gives us, the aurora borealis and australis, but more importantly, it acts as a magnetic shield that protects us from cosmic rays from the sun, which would otherwise obliterate our atmosphere. If we didn't have a magnetic field, there wouldn't be life here on Earth. That's why there's no life on Mars, because there's no magnetic field. It's obliterated its atmosphere, even though it's much further away. Not having a magnetic field means no atmosphere, which basically means no surface life. If you took away our atmosphere, the radiation level on Earth would increase by a factor of 10,000. It would be the equivalent of getting a full body CT scan every day. So it not particularly conducive for life on Earth. And as well, the night sky will look very different. Not because of the Milky Way isn't there anymore, but here's a picture of, if you Hubble Space Telescope, you take a beautiful deep exposure and you see there's a few stars in there, but most, lots and lots and lots of galaxies. Most of that is galaxies. That's what we see today using Hubble Space Telescope or James Webb Space Telescope, the Hubble Deep Field, for example. In 100 billion years, if you did the same thing, this is what you would see. You see, a handful of stars, but most everything else is gone. And the reason is, even though I haven't been saying anything, over this 100 billion years that I've been talking about, the universe is continuing to expand and continuing to accelerate, just like all of the observations suggest that it is doing. So during this period of time, galaxies are racing away from each other at high speed. And what does that mean? We talk about something called the cosmic light horizon. So it's not a perfect analogy, but it'll do for the time being. Here's Earth down in the middle. And from where we're sitting, we can look off to the left, if you like, back in time, 13.5 billion years ago. We can see a galaxy at the edge of our kind of visible universe, 13.5 billion years in the past. We can also look to the right and see a galaxy 13.5 billion years ago, that direction. And so that's what we call our horizon, which is basically the edge of the observable universe for Earth. But if I take this galaxy on the left and play the same game, well, they can look over this direction and see us because we're within that 13.5 billion year circle. And the one on the right, similarly, we could draw a circle around it and they could see us because we're 13.5 billion years. But the galaxy on the left can't see the one on the right because it is more than 13.5 billion light years away, if you like. And so at that snapshot in time today, we can see, if you like, our observable universe, but the guy on the left cannot see the one on the right. The one on the right cannot see the one on the left. And so all the while, galaxies are continuing to, get dragged along by this rapidly expanding universe, and galaxies then drop behind this light horizon. And so as time goes by, you see fewer and fewer galaxies because of that rapid acceleration of the universe. 1,000 billion years from now, stars are continuing to form and die and form and die. But every time you do that, you're using up gas. You don't get something for nothing. You create a star, you use up some gas, and you return some of it, but you don't return all of it. But in 1,000 billion years from now, trillion years from now, all the gas in the universe is used up. So that means no more stars can form. There's just no more fuel for forming stars. Those stars that do form will burn for quite a while. So you have to go forward in time 100,000 billion years. But the last of those shining stars, the ones that formed out of that last little bit of gas, eventually they do run out of fuel and they extinguish. So there's no more starlight at all in 100,000 billion years. The only thing that's left is the remnants of those stars, the crystalline white dwarfs that I talked about, but also the things that are left over from the stars that explode. Half the time, if you like, it'll be what's called a neutron star, and half the time it'll be a black hole. But that's all there is. There is no more. If you are around at that point in time, your optical telescope or your eyeballs are not going to help because there's no optical light anywhere to be seen. There's nothing to be seen. Go 100 billion years from now, what's left of those remnants, the vast majority of them have been tossed to outside of our galaxy into the cosmos. It's called two-body scattering, and you can just think of it as a slingshot effect. If you run enough time and enough time and enough time, you might say two black holes will eventually encounter each other, and one of them will swing by really fast and get a gravity kick and go tossed out. And a neutron star might come by a black hole, and again, it'll get thrown out. It's a slingshot effect. And so you slowly erode the remnants that are left in the galaxy and toss them out of the galaxy into the four corners of the universe as it continues to expand. So even though there's no stars that are shining, and 99% of those remnants of those stars have now been tossed out of our galaxy and are flying off by themselves all alone. And when you go forward even further, 1,000 billion years, I said 99% have been tossed away. The 1% that don't get tossed away by this point in time have fallen into the supermassive black hole that sits at the center of our galaxy and sits at the center of every galaxy. And so what's left in our galaxy is really just the supermassive black hole. That's all there is. And then the final thing, a billion years. The only thing, particles, if you like, carbon's not around anymore, oxygen's not around anymore. The things that chemical elements, hydrogen and helium, carbon, oxygen, are made out of are things called protons and neutrons. And even in that sort of period of time, we're getting a little bit speculative, but those protons and neutrons, we think, will eventually decay and give off a little bit of energy and leave behind something like an electron, or what's called a positron, but just teensy tiny little particles that don't really do anything, and a little bit of energy goes off. So the building blocks of life, the building blocks of planets, the carbon, the oxygen, and ultimately the protons and the neutrons, even they are all gone So those neutron stars eventually decay and just give off a few little electrons and some energy that goes propagating off. And then finally, the very last one, well, a billion, I'm not even going to read the number, but a really long time in the future, the only thing that's left is these black holes. All the neutron stars and white dwarfs, everything is decayed away. The only thing is left is black holes. But even black holes, we think, still kind of theoretical at this point in time, but it's an elegant, beautiful theory from Hawking, is that even black holes will eventually decay. And it's something called Hawking radiation. And it's a messy mathematical thing, but the thought process, the way to think of it is that we do know that according to the laws of quantum physics, particles and antiparticles can, and let's say what number one up here, they can appear and disappear very quickly. And again, it gets into quantum mechanics and Heisenberg uncertainty principle. Doesn't really matter. They're particle-antiparticle pairs that create and disappear very, very, very rapidly. And if you can create a particle-antiparticle pair, a positron and an electron, let's say, near the event horizon of a black hole, to create those particles, you probably know the equation. E equals mc squared. Energy on one side, mass on the other side. So in Einstein's picture, energy and mass are the same. So what you do is you create mass by stealing some of the gravitational energy of the black hole. And that's what, say, number three. If you like, think of it this way, if stealing a little bit of gravitational energy from the black hole, you create these two particles. If one of them falls in and one of them is able to escape, you've created mass. And to create mass, you've had to use up, some energy. And so you slowly erode the black hole by having these particles, antiparticles appearing right near the event horizon, steal a bit of energy from the black hole, the gravity energy from the black hole, to create this particle. And this is what kind of this Hawking radiation is kind of one way to think of this Hawking process. And again, we don't know for sure that this happened, but it's on a fairly solid theoretical background. So that is the thought process, is that on that sort of insanely long time scale, the last thing left in the universe, black holes, even they will decay, and you'll just have a few particles floating around. All the while during this period of time, all the observational evidence that we have suggests that the universe is just continuing to accelerate faster and faster and faster and fly apart. And ultimately, what is left is just some photon, a little bit of energy floating around and a few electrons floating around, spread out over effectively an infinitely sized universe, which has continued to expand exponentially on this sort of timescale, billions of years. This has a boring name. It's the heat death of the universe. The universe reaches thermodynamic equilibrium, but basically everything you hit absolute zero, particles are universes apart from each other in terms of distance, and the universe just continues to expand forever and ever and ever and ever. And that's kind of the depressing sort of end to it. There's no spectacular reoccurrence. Doesn't look like there's any sort of big crunch. The universe ends, not with a bang, but with a whimper. So it's kind of an anticlimactic ending, but on a positive note, trying to answer these questions about what the ultimate fate of the universe is and the ultimate fate of the particles that go into the building blocks of life. It's led to things like the internet that's allowing us to have this talk tonight, and the Wi-Fi that we're also using, that I'm using right now. Wi-Fi was invented trying to answer fundamental questions about, it's specifically evaporating black holes. It was trying to test exactly what Stephen Hawking suggested as to how black holes would decay. Never found any evidence for it, but the tools that they developed to try the experiment to see if black holes were decaying allowed, well, at the time, the Australian government to have the exclusive worldwide patent for Wi-Fi, which they had for like 15, 20 years and made billions off of it. But nowadays, we kind of lost sight of the fact that the Wi-Fi we use, there's lots of arguments as to exactly, who developed the mathematical algorithms. But that study of black holes and evaporating black holes is really the thing that seeded the Wi-Fi that we know and love today. So like I said, it's a rather sobering summary. I don't have some positive, uplifting message to pass on right now. The future is a little bit scary and a little bit bleak, depending on how you look at it. But I hope you enjoyed it. Hope you picked up a few things that you hadn't heard before, and happy to take a few questions here offline. Anything we don't cover tonight, you can always fire me an email as well, and I'm happy to follow up with anything that we don't cover tonight. So thank you very much again for letting me chat with you tonight.
That's great, Brad. Thank you very, very much indeed. We'll just hand over to Chris now for the questions and answers.
Hi, yeah, Brad, sorry, thank you very much. So I know that Pete's put a message in the chat, but if anybody has any questions, chuck them in the Q&A now, and we'll get them. Yeah, thanks for that. Tim will do a vote of thanks in a minute, but that was fascinating, although slightly depressing, and also interesting to hear the information on Hull University, although most people who are only fans of Blackadder will already recognise that Hull is one of the
absolutely. I
use
use
two
that
great
quote.
universities. Yeah,
I've grabbed it from YouTube, and I do use that in certain places as well. I love it, love it.
because obviously Oxford is a complete dump.
Yeah.
So I have one quick question. So you mentioned earlier on about Antares, and I think it was at WR104 being the closest crocodiles to the canoe.
Wow.
What are the possibilities that we might have an unplanned or a dynamic event that supersedes those, or is as a factor of on an earlier timeline?
Yeah, I am. Absolutely. Those are just ones that, we have even, over the last, what was it, 18 months ago, 2 years ago, all the excitement around Betelgeuse and whether Betelgeuse was going to go off, tomorrow or the next day, when we saw the light curve dropping by a factor of 3 over 12 months or something like that. So yeah, Betelgeuse could go off first. But yeah, those ones, like, I don't think there's any nearby ones. If you'd asked me this question 30 years ago, it was really uncertain because we didn't have a really good handle on the distances to the stars. And if you don't know the distances, it's hard to get the ages, and it becomes all really messy. I think because of things like European Space Agency's Gaia mission that was able to, it pins down the ages and the distances. You can get this beautiful 3-dimensional map of everything within any reasonable distance of us now. And so my understanding is there's nothing that we need to be losing sleep over. There's nothing that is far enough along the evolutionary process that is close enough to us that that we'd have to worry about if it explodes. So I think, yeah, Antares and Betelgeuse are two of the famous ones, but yeah, there's nothing in our immediate environment that is any, Alpha Centauri is not going to explode. We don't have to lose any sleep if we go out to that. There's a lot of debate as to how close something has to be to wipe out your biosphere, but the thinking is about 20 light years away is how close. Anything further than that, you're probably okay. Inside that, you're within the kill zone of the supernova. But there's nothing within, even 100 light years probably that's we need to worry about. Let's say. So yeah, we don't need to worry about that one. Everything else, yeah, we can worry about, but that one we don't need to worry about right now.
Cool, thank you. So Pete's got a couple of questions, and the first one is how often, on average, do gamma ray bursts?
Yeah, it's a really good question, and it's still very much a hotly debated one. The observations that we have right now are not particularly great at constraining the sorts of models that are out there. But if you take the best observational data sets that exists on gamma ray bursts and as a function of look back time, going back in time, and compare them with kind of the best models that we have for gamma ray bursts, the number that I saw not too long ago was in our local, I don't know, the local universe, maybe not necessarily our galaxy, but our local universe, something like 1 in a few thousand supernovae will be a gamma ray burst. And I'm sure you could probably find someone who says it's 1 in 10,000. Someone might say it's 1 in 1,000, but let's just say 1 in a few thousand. So if you thought of it, I don't know, in our galaxy, you get a supernova well, there's none nearby us right now, but it's roughly 1 every couple hundred years, probably if you average across the entire Milky Way, something like that. So you've got one every couple hundred years, and then one out of every 2,000 or 10,000 of those. So they're not super common, but that's roughly the sort of number that you see. I can see Bill's asked a good question as well. Has proton decay ever been observed, and what is the best estimate of the half-life of a proton? The answer is no to the first. It's still theoretical. The timeline for the decay is like insanely long. I forget what the number. I've now forgotten. Probably if you do a quick Google, what is the half-life of a proton? It is a gazillion years. So so some of what I just said is predicated upon the theories, the best kind of theories out there that suggest that might be what the half-life, if you like, would be. But that's still speculative. So it's a good one. I like that one.
Thank you. So Pete's put another one in. Is the big crunch theory now no longer a possibility, as dark energy and dark matter is still not truly understood?
So I think that is also one of the 64,000-pound questions. So there's a few. I mean, you can Google around, the fate of the universe. There's still a lot of theories out there that are being bandied about, and it is true. Something happened. Whatever, we can see in the observational data that there was some sort of transition from a dark matter dominated universe 6-7 billion years ago to a dark energy dominated universe. Something changed. We don't know exactly what, but something changed at that point in time. All the observational data we have right now, looking backwards in time, does suggest that the universe is going to expand, that there's a certain type of dark energy that it might be, and a certain type of dark matter that it might be. We don't have any belief that dark matter is going to change in any way, whatever it is. But something changed 6 or 7 billion years ago, where all of a sudden there was some phase transition where dark energy took over. So could there be another phase transition, depending on what that dark energy is? Could that happen in, X billion, gazillion years, where something changes in the nature of that dark energy? And so that is the big question that is driving these next generation of big telescopes, the dark energy survey, and a lot of these dark energy camera that's attached to the experiments are trying to zero in a little bit more on what the nature of that dark energy is. And I think within certain frameworks, models of dark energy, it could allow for some new transition that would, if you like, take away the dark energy as being dominant, and maybe gravity can then slowly win over again and slowly pull things back together again. So you can still salvage it depending on what the nature of the dark energy is. But I think it's getting more difficult to salvage it as I think the observations get better and they start to eliminate certain flavors of dark energy. There's still a lot of wiggle room around there. But I think it's getting harder and harder to salvage the big crunch, let's say.
Okay, thank you for that. Mark's put a question in, thank you. You said in 2.5 billion years, an Earth day would be 25 hours. Would the Earth's time to orbit the sun change, or would that remain the same? And would we now have, for instance, 350 hours, 50 days in a year?
Yes, I think so what I don't have what is a good question that I don't know the answer to is, we can measure how fast the moon is moving away from us. We've got these beautiful mirrors on the moon, and we can measure it with a laser. So we know what the drift is, and it makes sense physically. The Earth is not drifting away from the sun at the same rate that the moon is drifting away from the Earth. So I think on that sort of time scale, on that time scale of billions of years, it's probably not going to change in any dramatic way at all. The length of the year, if you like. So even though the moon is drifting away, that influence, that anchor that the moon provides to the Earth is not as strong as the anchor that if you like, the Earth provides to the sun. So yeah, there probably is some teensy tiny little thing, but it's probably lost in the noise, to be honest.
Cool, thank you. Because they're coming in thick and fast at the moment.
Oh, that's a good one. I like that.
Bill's just going, my life membership certificate is valid until the big crunch, so will Sigma be stuck with me for even longer than when the certificate was issued? I think that one probably has to go to Pete to answer that one. So the chairman can answer that one after the break.
It'll be
we've got
fine print.
we've got a couple that have come through on the webinar chat. So Rich has asked, question for Brad, would you therefore say we are living in the best of times? A quote from Charles Dickens by the sound of it.
I think it probably depends if you're optimist or pessimist, glass half full, glass half empty. I don't know. It's probably more of a philosophical one, but I think we're living in a very good time in the sense that we do have more or less access to almost everything in the universe right now, if you like, thinking of it that way. The James Webb Space Telescope and the next generation radio telescopes, you know, are this acceleration phase as things drop behind the cosmic horizon. We haven't lost sight of too many things yet, let's say. So it is a best of times in some sense that we do have access to an incredible look back time that, and certainly, you know, technology wise, compared to thinking back to when I was starting my PhD 30 odd years ago, I mean, it's incredible. I mean, the unanswered questions back then, we've made such strides in such a short period of time. So for me, I mean, the heady excitement of accelerating universe, the determining the expansion rate of the universe, these were things that just 30 years ago we had speculations, but we didn't have the answer to. All the discoveries around exoplanets, these are all super exciting times. So from in a small, my own personal sense, yeah, it's the best of times. At the same time, as funding disappears, it could also be the worst of times. Yeah. So yeah, we talked about that earlier. So.
Rich has got another one. What is the range of a gamma ray burst, or is it infinite?
I mean, whoops, where did we go? Sorry, lost you there. No, like everything, it drops. It's called the inverse square law. So as you just like sound, if you go twice as far away, the sound isn't a factor of 2 lower, it's 2 squared. It's a factor of 4, it drops off. Or a flashlight, and you shine it and you measure how bright it is. If you move that flashlight 10 times further away, it's 10 times 10 weaker, it's 100 times weaker. So sound, magnetism, electricity, light, they all drop off as the square of the distance. And it's the same thing with one of these gamma ray bursts. They're incredibly powerful, but the energy, even if you focus it into a tight beam and fire it along, the energy does drop off with the distance, because this cone is spreading out, and so the energy, if you like, per square meter, per square centimeter, whatever you want, does drop off with the distance. It's just that its effect is much longer because it is focused, but it doesn't go off infinitely. It does drop off as I say, the square of the distance.
Cool, thank you. Ray has a question. Could quantum fluctuations not lead to a second Big Bang?
Well, yeah, you're getting to, at that point, you're getting to a degree of, I'm sure you can play around with the initial conditions that exist in those primordial fluctuations that could lead you to a very different sort of universe. But it does become the problem with a lot of these, well, it's not necessarily a problem with these sort of things, is that there's no way to test them, so they become mathematical. And so so I'm sure there'll be some spectrum, if you like, of primordial fluctuations, where if you did it randomly over and over and over again, there is probably some combination of fluctuations that would lead you to a very, 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 very different universe, because it is sort of a random process in how these fluctuations are sitting there. But you're into hardcore theoretical physics and mathematics, which I come in kind of where a few minutes later when the chemical elements start to form, because that first tiny fraction of a second that's the playground of mathematicians rather than astronomers. So it may sound like a cop-out, but I try to avoid that one. That topic is too scary for me.
Thank you. And this is the last one. Again, this is from me. If anybody else has any more, you've got about 2 minutes to chuck your question in. But when you talked about the expansion of the sun, if we haven't done a really good job of destroying the Earth ourselves, which we're obviously doing a pretty good job of at the moment, is there a possibility that a Goldilocks zone would move out as far as Mars? And as long as we can get there, then it would aid life on Mars, or do the timelines just not work?
Yeah, so I think in terms of temperature, yeah, and there's a lot of speculation about exactly how big when the sun becomes a red giant, exactly how far it's going to go. So there's a lot of wiggle room in some of the numbers, but yeah, in principle, it very much would lie, depending on the sort of model that you put into the red giant, it would live in that Goldilocks zone. You would still like to, well, okay, if we are around in X billion years, it would be the right temperature, but you'd need somehow to reignite the magnetic field to allow you to melt off carbon dioxide, CO2 ice, and water ice, and try to establish an atmosphere. Now, probably if we were around, we would have the technology to create maybe not restart the magnetic field like in the film The Core, but maybe what you'd be able to do is create an array of satellites that sit between the sun and Mars, and basically create a magnetic shield there rather than creating it within the planet itself. So I have seen papers out there, people speculating about how would we construct, at least in a theoretical sense, how would we construct a magnetic shield that would sit between Earth and, if for some reason our magnetic field turned off and you wanted to create a magnetic shield, how powerful would it be? Where would you place it? People have given some thought to this. And I'm sure if you're around in X billion years, we'll have the technology to create an artificial magnetic shield between Mars and the sun.
Cool. That's one for Elon Musk or his grandchildren. So last one, I think, from Martinus, apologies. If the sun expands beyond the planet, what would happen to the orbit of the planet?
So it's an interesting one. For the planets that are further away, effectively nothing happens, right? If the sun expands really far and Mars is still outside that, Mars just keeps going around basically in the same orbit, because it's how the mass is distributed inside of it doesn't really matter. It could be a small little star that weighs 1 solar mass. It could be a big bloated one that weighs 1 solar mass. If it does expand out far enough that it envelops Mercury or envelops Venus or envelops Earth, as it's slowly expanding, it all depends on the rate at which, at the time as the sun is expanding as a red giant, it's blowing a wind. It's losing some of its mass, and so if it blows off 20% of its mass while it's expanding, let's say, that means it's lighter, which means the planets drift out. And so there is some debate around Earth and Mars as to whether the sun would lose enough of its mass while it's expanding. Would it lose it fast enough that the orbit could adjust and sort of drift out a little bit because the sun is lighter than it was at the beginning? There's a lot of model dependencies in there. I think the majority of the work would suggest that it'll sweep up Earth before Earth has a chance to go out far enough, and the tidal effects and the atmospheric effects would be such that it would incinerate the Earth. But if you're an optimist and depending on how you work the numbers a little bit, you can blow off the mass quick enough that the orbit of the Earth can adjust accordingly so that it doesn't get incinerated. So it's still debated, but yeah, so there are those who suggest that Earth could survive if it drifts out fast enough while the sun is losing its mass.
Sweet. Thank you. I think that is all the questions. So again, thanks so much, Brad. Fascinating. I'll hand you over to Tim for the vote of thanks, and we'll be in touch. Thanks so much indeed.
Thank you.
Thanks, Chris. Just if you can bear just a general extra question from me, Brad. It sounds as though you're doing tremendous work in encouraging students to take up the study of astrophysics and space science. Not necessarily, I suppose, not necessarily all of those when they graduate will take a job in that. But would you
Absolutely
agree?
not.
Would you agree that the training that you get in studying astrophysics, astronomy, space science, actually stands you in good stead for a wide range of careers? And I've always felt that's a really, it applied when I was at uni, and I'm sure it probably still applies today. Would you agree?
Yep, that's the key. You know, when I'm going into schools and colleges, I'm not necessarily selling them on careers in astrophysics. The stats are, you know, 1 in 10, 1 in 10 might pursue that as a career. And that's fine. It's, you know, ultimately it's physics, right? It's, even though it's got astrophysics in front of it, it's physics. It's the same physics that people are doing with lasers, material science, just applied to stuff up there. So it's the same fundamental skills. But you can look at the employment rate of physicists and astrophysicists. It's higher than computer science. It's higher than engineering, because the same jobs that engineers can go for, physicists can go for. The same jobs that computer scientists go for, physicists can go for. We develop data mining tools. We work with massive data sets. We use AI and machine learning to analyze massive data sets. 3 of my students in the last year have gone into medical physics with the NHS because they've been analyzing galaxy images and how they're compact or extended or asymmetric or clumpy the galaxies are. They apply the exact same tools to radiograms now and tumors and characterizing the structure of tumors, because, you know, data is data. So particularly for imaging science, it's dead easy to move between geoscience and some of those. But anything that's number crunching, and data science jobs are, you know, they're everywhere, fastest growing employment sector. So as long as they're working with data and data analysts, they seem to be highly marketable. And that seems, it's not Hull, it's not Oxbridge. Our employment rate's the same as Oxbridge or Edinburgh, because physics is physics is physics. So, to be honest, it doesn't matter. I'm not supposed to say it, but it doesn't matter if you go to, you know, I worked at Oxford for years. Employment rate's the same as graduates from Central Lancashire, because everything's accredited by a professional body, the Institute of Physics. So it means physics at Hull is the same as physics at St. Andrews. I mean, that's being somewhat flippant about it, but there's not a huge difference in that sense, and there's not a huge difference in the employment rates, and they are high because of the skill set that you acquire.
Yeah, excellent. And I was interested in the history of Arthur Milne. I have an interest in the history of astronomy, and in our newsletter each month we post a list of anniversaries, astronomical anniversaries, i.e. when famous astronomers and scientists were born and died. And when I heard about your talk, I added Arthur Milne into our February anniversaries, because he was born on the 14th of February.
I'm gonna have to make a note of that. I'm gonna have to I'll have to send a message down to, oh my God, yes, you're right. Okay, thank you for reminding me.
And
so I still stay very much in touch with his daughter, and especially his granddaughter as well. But they're both just amazing, strong personalities, both of them. So I'm leaving that open now and making a note to remember.
and he was born in, I think, 1896.
1896.
And I'm always intrigued to see, for whatever reason, when scientists have similar birth dates or are born about the same time, or one's born and another dies, that, you know, about the same time. And it's just statistics, but I was intrigued by the fact that on the same birthday, 14th of February, Fritz Zwicky, the well-known astronomer,
Discoverer of dark matter. So
discoverer of dark matter. And I believe, did he not coin the word supernova as well? And dark matter he thought of as an idea back in the 1930s.
He was way ahead of the curve on dark matter. Yeah.
Yes. Yeah, absolutely. So I was quite intrigued. So both of those are next to each other in our February anniversaries. So any members who haven't had a look at it, go and read it. It makes interesting reading. But look, Brad, that has been the most fantastic talk. Really, I agree with Chris. It's a bit scary from that point of view, but just mind-boggling. And as I was watching, I was thinking, goodness me, who's going to be around then? But of course, who knows? But I really must thank you on behalf of Sigma for putting together such a fantastic and interesting, fascinating talk.
Thank you so much.
And Zoom's a great thing, but and so it's been great to have you there. But if you're ever passing this way, as you know, we would very much look forward to seeing you in person.
Promise you that we will get up there at some point. And yeah, my family, it's not that far north, but my grandparents are from Glasgow. I have a soft spot for Scotland as a whole. We've been up skiing a couple times around Avonmore, and we've of course done a few tours of some of the single malt distilleries.
Wow, absolutely. Talking of which, just as by way of our appreciation of the talk that you've given us, I don't know if you can see. I'll probably hold it against my. I'll just turn the camera down. And hold it
I think I see it. There we go.
Yeah, there's a tumbler inscribed Sigma. They're worth millions.
I can imagine.
You can. So Rich will get hold of your address to send that to, and we'd like to give that to you.
That means a lot to me. Thank you.
Best wishes
so much.
And fill it up with something that is of taste to you.
I promise I will.
but in the meantime, thank you once again.
No, thank you so much.
An inspiring talk, and very much. I better put the camera back up. Very much look forward to seeing you as and when.
Yeah, you can drag me back again next year even if whether it's in person or online. I'm always here. I had a great time chatting with you tonight.
And are there telescopes and so on to look at if I'm ever down, or any of us are down Hull way?
I mean, what we've got on campus is probably not going to be half as good as what most of you have got in your back garden. I'm afraid to say. There is a couple of astronomy societies near the East Riding Astronomy Society, which is not too far from us. They've got a beautiful facility about 4 or 5 miles north of here in a small village. They meet the first Monday. So I'm going to go out there Monday and drag my kids out to, weather permitting, see something. But they've got a really nice setup in terms of it's close proximity, and it's right on the way home as well. So it's perfect.
Great stuff. Oh, well, look, thanks once again. And I'll hand back to Pete.
Yep, thank you very much, Tim, for doing that. Brad, thank you very much. And just say you're always going to be welcome up here. Just give us
I'm going to be back in touch again.
We've got my phone number. Give me a call if you're coming up. Let us know, and
I'm gonna have to run because I've been sent a message from my wife to pick up shopping on the way back. So if I'm going to make it to Tesco before they close, I'm going to have to do a runner.
No problem. We will let you go, and thank you very much.
Thank you so much.
We'll be in touch.
Great seeing you.
Okay. Right. So we'll go for thanks, Dave. We'll go for a quick 10-minute break now, so we can get set up for the second half. Coming up in the second half, we have got Ray's going to do a little bit about the workshop that's coming up on Sunday for the astrophotography workshop. Then we got a couple of members' photos. And then after that, we've got Mick doing the Morning Sky at night. And I'll be finishing off with a bit of club news. We'll probably finish off just after probably 9:20 to 10, something like that. Okay, so for now, we'll have a quick 10-minute break, and then we'll be back. So we'll be back just after 9:10. Okay, we'll see you in a little while. Okay, welcome back everybody, and to the second half of this meeting. As I say, I'm just going to hand over to Ray now, who's going to give us a little bit of information on the workshop that's coming up on Sunday. Ray, if you're there, over to you.
Hi folks, just a quick one really about Sunday. The doors will hopefully be open around about 2:30, so myself and some of the members of the committee will be there to get things set up with 3 o'clock starting on the cards. But if you could get there sort of 5 to 10 minutes earlier, it'd be greatly appreciated, because we've got a lot to get through and only a limited, finite amount of time at the venue. So if we could everybody get there sharpish. And secondly, there's nothing worse if we're in full flow and somebody comes in 5, 10, 15 minutes late, then it's a bit disruptive. So just to say, if everybody could get there sharp and ready to go by 3, it'd be much appreciated. Hopefully we'll all have a bit of fun with this, and at the same time maybe learn something. Like I say, this is an interactive session. It's not death by PowerPoint. Hopefully it's hopefully people can come along and share their own ideas and experiences, and we can all benefit from that. So looking forward to seeing you all there, and that's really it. So if everybody could just get there on time or a bit early, it'd be greatly appreciated. So that's all from me. So back to Pete.
Okay, Ray, thank you very much. Yep, so just remember that the workshop is on Sunday. We've got 16 people signed up to it already. If anybody else wants to join, please just get onto the Spond. I know some people have had difficulty putting a fee in for this. No, that's not a problem. If you can just let me know you want to come along, if you haven't already signed up through the Spond, then or through an email, then I can add you to the list, and you can pay on the day. But we just need to know a number so we know how many tables are set up. So please, if you are coming along and you haven't signed up yet and you want to come, just let me know. Okay, right. So we will now head on to the members' photos. As I said, there's not that many of them come through this month. Probably a good reason for that is that the weather's been pretty awful. And it's mainly, I think it's mainly mine this month, but hey ho, so be it. So a nice collage there of the ones we had come in last month. So this is the one I took on New Year's Day. Funny enough, I didn't have too much of a hangover New Year's Day, and I was out quite late. It's quite good. How to say, this is the Pleiades, or M45, Messier 45, the Pleiades, or probably better known as the Seven Sisters. But as you can see, once you get a telescope or binoculars onto the Seven Sisters, there's a lot more than 7 stars that you can see with your naked eye. So once again, I took this with the Door 2 Smart Telescope. It's 415-second frames. I was hoping to get a few more, but it did go a little bit hazy with clouds, so I had to actually stop at one point, and I stopped at the 400 frames. So it's 415-second frames. I've gain set at 80. And as I say, it really does. This little dwarf telescope is amazing what you can get from it. They say even when it was live stacking, the image that was coming through, you can actually see the gassiness around the around the stars. And then once I put it through Cyril, I managed to darken down the background a little bit, and it really brought it forward. I say this is all the sort of things we're going to be trying to cover in the next few workshops of how to get these images and how to process them. This one came in from Mark Betson once again with the Dwarf 2 Smart Telescope on the 23rd of September. So it's going back a bit. I think it's probably the last time we've seen the sun, to tell you the truth, apart from today. To say, wonderful area of sunspot activity just there, right in the center. And you can see some, the sunspots here, and another low down there, and another big area of sunspots at the top there. Absolutely wonderful how this little thing works. Obviously, if you're observing the sun, you only ever do it when you've got the proper filters on. And they say the Dwarf 2 Smart Telescope comes with the solar filters, so if you don't put them on, it actually ruins the camera. So. Okay, next is this one, and I say this was another one I took once again with the Dwarf 2 Smart Telescope. Only got 399 frames. I was hoping for a lot more, but once again, there's such a small gap in the clouds that it started to cloud over again, and I was starting to lose the images that were coming through. So I stopped at 399. I was hoping to get way up to about 700 images of this, but there we go. You can only do what you can do when the weather allows. So this is M81 and M82. So Messier 81 and 82. And I say Messier is, for those of you who don't know, he was a French astronomer, and he was actually a comet hunter. And he kept coming across all these faint fuzzes, as we call them, in the sky. And he kept coming over and over them. He was getting a bit annoyed that he was mistaking these for comets, and they weren't. So he made a catalogue of them. That's the Messier catalogue. Let's see. Spent so much time doing that. I don't think you ever actually found a comet named after him. So here we got, say, M81 and M82. You can tell the difference between each other because M81. I'm going to get this right. M81 doesn't look like a 1, which is that one, and with that one there, and M82 does. Okay, that makes sense. Also, I noticed when taking this out that, and drawing a little bit of detail out, you also have this faint galaxy down here as well, which is NGC 3077. Okay, so it's marvelous what you can get with this little dwarf telescope. And I think, no, I got one more. Remember last month, Mick gave us a challenge of Kemble's Cascade. Well, I thought, well, I'll give it a go. Why not? And it just about fits into the frame of the Dwarf 2 Smart Telescope. So Kemble's Cascade is, you can see this, we've got bright stars there, bright star there, a cascade of stars running right down to the star cluster at the bottom here. Can't quite remember the number of the star cluster. I should have put it on the title there. I do need to do a little bit more work with this. It's still a little bit red in the background, but when I tried to take the red out, I did lose the color of the stars. So I'm going to have to try and do a little bit more with that. But as a first go, I think that's a pretty good image. So say that was 469 frames at 8 seconds, and I have a gain set at 100 on that one. I think that was a week after New Year. A couple of a couple of breaks in the cloud to give us a chance to do some imaging, but not a great deal. But hopefully, as we come into spring, the nights will get a bit better. Don't forget, if you've got any photographs you want included in this section, please do just send them through to me. I normally send out a little email just for the sort of meeting, and as I say, I'll get them included in this for you. Don't worry about how good or how bad they are, just send them through. It's always good to see people's learning curves on this as well, so have a go and send your pictures in. Right, so now it's over to Mick for the Moray Sky at Night.
Thanks very much, Pete, and thanks, well done for the Kemble's Cascade. It must be one of the few times I've actually had I'm just trying to find where is it? Go. Yeah, one of the few times I've actually had an image back from challenges. Okay, welcome to tonight's Moray Sky at Night, and this night sky guide tonight will be a supplement to what's in the night sky guide that I've sent out already. As usual, I'll start with the planets and the moon, and then I'll do a tour of the portion of the night sky and finish off with a brief mention of comets. So the planets, the inner planet Mercury is too close to the sun to be visible in the dawn sky, as you can see here. So I've put it to tomorrow at 9 AM. A bit late because the sun's up, but if you go any earlier, they're below the horizon. You're obviously not going to see them. I've put the atmosphere on, you can see they're all washed out. But it's just to give you an idea of where they're at. Venus, that's still bright, at magnitude of -3 in the morning sky, but it's very low in the horizon. Mars, as you can see as well, too close to the sun. Go to the evening sky. Come on, 17. For the next planet, Jupiter, so that's moving slowly in Aries at a magnitude of -2.3, so it's nice and bright. Saturn remains in Aquarius, as can be seen here just after sunset, before it sets. Uranus is across here next to Jupiter in Aries at a magnitude of 5.7. Neptune is in Pisces at a magnitude of 7.9. That's over here somewhere. No, can't find it. No. There it is. Right. So for some possible photo opportunities with the moon, it'll take us to the 12th, 7 p.m. So the crescent moon on the 12th will be close by Neptune. And moving through to the 14th, 15th, the moon will be passing Jupiter. They'll be next to Uranus. 16th is going to be right by the Pleiades, M45, or the Seven Sisters. Continuing, 17th it'll be 10 degrees north of Aldebaran in Taurus. And then through to the 20th it'll be next to Pollux, one of the twins of Gemini. 23rd it'll be down by Regulus. And if we move to towards midnight, it's going to be between Regulus and Algebra in Leo. And that's pretty much for the moon this month. So now moving on to our night sky tour. I'll go to the middle of the month, which is what I've got all the charts set to that I've sent out. Just gives you a rough idea where things are. Go to 9 p.m. So meteor showers, there are no meteor showers worthy of note in February or March. As we can see, by early February, the Colossus Orion is across the meridian. The belt stars guiding us around the late winter sky. To the northwest, we have Taurus, of course, the red giant Aldebaran, which sits in the Hyades, which is this V-shaped asterism of stars here. Aldebaran isn't actually part of the Hyades because it's a lot closer than the other stars. Going the other direction to the southeast, we have Sirius, the dog star, glittering away there in Canis Major. The brightest of all stars due to its relative proximity of 8 light years. So taking a line from Rigel here at the bottom right of Orion, up through Betelgeuse, if we continue beyond the same distance, we get to Gemini the twins. And in amongst these, we have 3 contrasting planetary nebula. So just southwest of the multiple star Castor, Alpha Geminorum, and north of Iota, which is this one, and about here, we have a challenging planetary nebula, NGC 2371 and 2372. So with its outer extensions, some feel that it looks like Darth Vader's TIE fighters from Star Wars, but it's usually nicknamed the double bubble. The central star is prominent, although it is quite faint at 14th magnitude. To see this nebula well, you will require an oxygen filter. Next target, NGC 2392, the Escuma Nebula. To find that, we head to Pollux, come down to this waste star here. Which is a double star, Delta Geminorum, or Wasat. And just to the southeast, we'll find this bright star here, 63 Gem. And if we head down to this next star, if I take this away, you'll see there's like a very faint one next to it. That is the Eskimo Nebula. It shows a high surface brightness at 9th magnitude in a roundish green disk. Known as the Eskimo Nebula because of its resemblance to a furry parka. So this bit surrounding a chilly face. But it's quite often described as the clown face, or even the Lion Nebula, where this parka is becoming its main. It's bright and rewarding, with an unusually bright central star surrounded by a complex inner ring and a fuzzy outer haze, as you can see. This was the first target of the repaired Hubble telescope back in December 1999. And we're actually looking down a cylindrical nebula directly to the pole of the central star. That's what makes it so bright. It takes magnification well, and on the best clear nights it shows detail, shows great detail. The third planetary nebula we'll look at is the Medusa Nebula. To find it, we head to Lambda Gemini, so back to this waist star and down this leg to the kneecap. Just show you some artwork to prove it. There we go. And what we're looking for, if we find the moderately bright open cluster NGC 2395, which is just down here. Oh, wrong button. So we're in an open cluster here. And if we just head slightly further south, we find the Medusa Nebula. It's quite large, being over 10 arc minutes across, but that dilutes its deceptively 10th magnitude light, so it really requires large aperture telescope and a perfectly dark sky, along with an oxygen filter for some success. So bypassing excuse me, heading south, bypass Canis Minor, and in this area here, or to find another way, we can come to the west, to the east of Betelgeuse to find the Christmas tree cluster. So the cluster is embedded in a fox fur wrap, which you can just vaguely see here. And the dark nebula silhouetted against emission nebula. So the best known, there's molecular clouds known as the Cone Nebula. So it's actually an upside down Christmas tree as you look at it. So this is like the top star, if you like. And here we have the Cone Nebula, the apex of the Christmas tree. We also have a couple of nebula just adjacent, NGC 2245, sorry, 2247. And we also have further south, NGC 2244, which is the Rosette Nebula. So this cluster has several O-type stars, which are super hot stars, generating large amounts of radiation and stellar winds. The age of this cluster is quite young. It's estimated at less than 5 million years old. Moving further east along the ecliptic, oh, come out too far. We come towards Cancer, and down the bottom here we have the Golden Eye cluster, Messier 67, and also, of course, to the center of Cancer we have the Beehive cluster, Messier 44. And I actually had this on my list, but further north, of course, we have Ursa Major, and there's an even closer gathering to us, the M81 group, which Pete was showing you images of. To find that, so we take the plough here, and from Do and Fecta, starting Fecta through Do, and out about the same distance around here. We have Bode's Galaxy, M81, and we also have the irregular galaxy, the Cigar Galaxy, M82, and an atypical elliptical, which is a kind of galaxy the professor was telling us was going to occur when we merge with the Andromeda Galaxy in, what was it, 5 billion years time or something. Okay, so that's my night tour finished. I'll just quickly mention comets. Get back out of there. What I'd like to do, I won't go into any detail about the comets other than showing you roughly where they are. And what I want to do first is show you how to add the comets in the stellarium, because I didn't show you that last month. So it's fairly straightforward. What we do is we go to the astronomical. No, we don't. What's the next bit? Sorry. Go to the config editor and select plugins. If we scroll down the bottom, we want Solar System Editor. Click Load at Startup, then go to Configure, and we want to configure the solar system. Then we select this, Import Orbital Elements, and then we want comets. You can go later and add asteroids if that's your favourites. And then we want to select a list to get them from, and we want this one, NPC's list of observable comets. Get elements, and this brings up this page. So we want to add new and existing and update orbital elements. And then you can go in here, and once you know the comet you're looking for, normally start with a C, like these ones. I won't actually add any just now, but you just click Add Objects, and that's it. So that's what to do if you click either Control F or Command F to bring up your search bar. If you look in there for your comet and you can't find it, then you have to go and add them the way I've just shown you. There is a video on our YouTube channel that you can go and look up that explains that if you want to go over it again. So now, how do we see where they're at? Well, apart from looking for it like tonight, what you can do is click plot an ephemeris. So that shows you where it's predicted to be. So if you go to this astronomical calculations window, ephemeris, and you can select in here. So I've got 2 out of the 4 that are mentioned in my notes that I sent out. And what you do is you click what you want to see. So line, markers, dates, magnitudes, how many days or hours you want, the steps. And this 1 and 2 here, so the first one will be in yellow, so it's 12P1, and the 29P1 will be a purpley type colour. So you click calculate, and it basically comes up with this information. You close that and then go and find them. So there's the first one. What it shows, the date is a month is in Roman numerals. So that's the 15th of Feb. I didn't actually check the date, did I? That's because I'm on the 15th here, stand by. What I'll do is go back and change that to put the first. I'll put the end of March 30th, that's close. Clean up, redo that. Right, there we go. So that was the first, so the second will be around here. Come on. Stellium's not playing. So this shows you where it's at anyway, or where it's predicted to be. So the magnitude 9.39, of course, as the magnitude comes down, then it's getting brighter. So you can see where you can look for that in the sky. And I'm fairly certain this. Ah, do you know what it is? We're on the 15th, so we have to find the 15th on this line. There we go. There's the information there for you. So we'll go and look for the other one, which is up here, Cancer. So that's going this direction from bottom left to top right. So at the 1st of Feb, click about the 15th. Oh, should we go there? There we go. That gives you some information on it. So I won't bother doing the other two. I'm sure you can have a play in Stellium yourselves and using the information I've sent out in the newsletter. And that's me for this month, Pete.
Okay, Mick, thank you very much for that. To say that one comment there, it looks like it's going to be naked eye visibility then. Magnitude 5.7, I see.
Yeah.
So that's going to be a good one to look out for. The other one might be a bit of a challenge at 15, but you never know.
Yeah. Yeah.
Okay. Right, okay. Cheers then, Mick. Right, so I'll just finish off with a little bit of club news. As I say, I did put it in the newsletter, but I'll just explain it again. We had a meeting with the Lambride, well, I think he's the chairman of the Lambride Community Centre this other Sunday. Tim, myself, Stuart and Mick were there. And so they're very keen to keep us there, and they've offered us, some very good benefits, to tell you the truth. Start with access to the hall at all times. Now, this means it's going to make observing nights much comfortable. This has always been a problem when we've been out observing. Is if it does go cloudy and you want somewhere warm to go, just to warm up for 10-15 minutes. And 1 second, something just popped up on my screen there. Sure, my video is running. Give me 1 second there, please. I'll put my video on. I must have hit it twice. Gotcha. Sorry, my video wasn't on. Yeah, so as I say, that there's always been a little bit of a problem of being comfortable while we're out observing. But what they said we can do is we can get access to the hall at all times, and which is going to be great because it means we can get into the kitchen, get hot water going, get some teas and coffees going, and also we've got access to the toilets, which has always been a big problem. The other thing they said is they're going to try to stop any crossovers of other meetings in the hall. Last year we had a couple when the football club were in there. They can't promise, but he's going to do his best to make sure that doesn't happen again. Okay. So it's all looking promising down there. We can also use the small meeting room free of charge. Oh yeah, let's say the nights we're observing, we can use the toilets free of charge, which is always a positive. Let's say we, at least we can get access into there. So all good things. The other thing they said was that if we do any sort of outreach, public outreach for the local area, we can have the hall for nothing, and they'll help advertise the event for us as well. So that's all good. Now I want to go about the telescopes we have for hire. At the minute they are just gathering dust. I think Rich is actually thinking about taking the mirror at the bottom of his and turning it upside down and putting plants in it or something, because he's been in this house for so long. No, he's not. I won't let him do that. there's any new members out there, I mean, we have got two great telescopes that you can use: the Dobsonian refractor, 6-inch reflector, 6-inch reflector. Nice and easy to use. It's just a Dobsonian. Plonk it down, put an eyepiece in, and away you go. We also have the refractor, 3.5-inch refractor, which is on an equatorial mount. A little bit more difficult to use because of the mount, but we'll show you how to use it. I would like these telescopes being used. You can get them for a month, and say we charge us £5 for the month. It just covers any damage that might happen to them or anything that needs sort of replacing. And obviously, if it's cloudy, you don't get to use it. You get your fibre back. Okay, so if you want to borrow one of these telescopes, please do just contact me or one of the committee, and we'll get them out to you. Okay. There's no point in them just sitting in a corner gathering dust. Outreach, we've got some a couple of little outreaches of contact. Sorry, a couple of clubs have contacted me for a bit of outreach work. One of the clubs, but I've emailed them back and heard nothing back yet. But if you've got any, if you're members of other clubs who want talks or anything like that done, please let us know and we'll try and arrange something for your club. So we don't charge anything for it, but if you want to make a donation, all well and good. As we have a few new members, I think I should explain about the observatory and the observing sessions. So any new members here, you probably don't know, but we have actually got a 2.7 meter dome observatory, and inside that we have the Williams Optics 132mm refractor, which is an absolute top end telescope. It's all donated equipment, and as I say, it's there for members to use. What you have to do is do a short training session. It takes about 15 minutes, that's all. And I'll put the training sessions out on Spond. It's the only way I can organise it because of the size of the observatory. We can only have, for the training sessions, we can have about 3, perhaps 4 people in there. For the observing nights, you're looking at 2, possibly 3. So do the training sessions, and then you get transferred onto the observatory observing Spond page, and then when it's clear, we can get it opened up. As I say, the observatory is in Fochabers. All you have to do is just get that training done, and then it's free to use. It's not free to use; it's for you to use. Don't be afraid of it. I will always be on hand to give you a bit of, a bit of guidance if you're stuck. Let's say once again, we charge a little fee, minute fee of £2 per person per night for using it. Let's say once again, that just covers if there's any damage happens to the observatory or the telescope, we can get it repaired. I say, don't be fearful of using the thing. It's a relatively easy telescope to use, and I have just put a Telrad finder scope on it. I did mention this in the WhatsApp group. I'd never used one in the past. I've used different types of finder scopes, but this Telrad is absolutely brilliant. I've got it lined up. You look through it. There's a dot. There's a small circle, a larger circle. The center dot is obviously smack on. The smaller circle is 2.5 degrees, and bigger circle is 5 degrees. It's about, I think that's right. And I say, you look through it, line it up on what you want to look at, and it's there in the eyepiece. So I was quite amazed how well it worked. Excuse me. And it's got a heater on it as well, so it doesn't chew up. So yeah, if you want more, any more information, just sort of let me know. Don't forget to invite a friend. If you've got any friends that are keen on astronomy or want to learn a bit more, just bring them along, or let Mick have their email address, or get them put to contact Mick, and he will send out the details for the next meeting. All right. And I always say, don't get your club, not my club or the committee's club. If there's anything you want done, or if you think we're doing okay, let us know. Or if there's something you think we could be better, please let us know again. So don't forget the next meeting. We've got an extra one on Friday, the 16th of February. That's Hazel Collett. You might remember Hazel. She was the organizer for the BAA event that was held in Elgin, what's that, 2 years ago now. I'd say that's promising to be a very interesting talk with the beauty and violence of the sun. So I think that's it. So with that, I want to thank Brad for his fantastic talk. How it's going to end, we probably never will know, because we may not be here, but who knows? We might be, might be an interstellar species by then. Chris Randall in the Q&As, Tim with the vote of thanks, and being our latest honorary member. Mick from More Sky at Night, and all you good people out there for joining us, and I hope you enjoyed the evening. So for now, it's good night from me, and it's good night from the club. Good night, everyone.